This part of the tutorial is about action synthesis. Saying differently, is about methods of computing valuations of parameters which correspond to sets of actions. So far, you learned about Petri nets with discrete parameters, time Petri nets with timing parameters. Let us now address synthesis of actions. Let me start with a short intuition behind the subject I am going to discuss. As you already know, there are three situations in which you can use parameters. Parameters can be in a model, parameters can be in a formula, and parameters can be in both, in a model and in a formula. For this presentation, I am going to concentrate on the situation when we have parameters in a formula. That means that we can specify systems using formulas which in fact ask about evaluation of these parameters with sets of actions. And this is also a way, in fact, of asking questions about models. If we think about standard model checking approach, which is about finding whether a formula holds in a model, now we will be asking a question, for which valuations of our parameters our formula holds in a model. But that means asking a question, which actions can stay or which actions should be removed from a model to make the formula in question to hold in the model. So let's start with a definition of a model which I am going to use in this presentation. And these are mixed transition systems which were defined by Pescher and Raimondi 11 years ago, and they are called Kripke structures with action-labeled transitions. These are just 5 tuples, as you can see here, which are composed of a set of states S, the initial state S0, set of actions, and this is a new component if you compare these models to standard Kripke structures, because in standard Kripke structures you in fact are not using actions, and also transitional relation is now a bit more complex, because this is a subset of the Cartesian product of the set of a set of states, set of actions, and set of states. So this is a labeled transition relation. We label all transition with actions. And because we won't assign formulas to the states of our model, we need to have propositional variables. And so this is a component of our model. And in order to know which propositional variables hold over which states, we have a labeling function which assigns with every state a set of atomic propositions which are assumed to hold over that state. And a bit differently than in the standard case, we are not going to look at infinite paths, rather at maximal paths, in order to give semantics to the logic I'm going to define in a while. So path P in our model M is a maximal sequence of states and actions such that for each two consecutive states, the action which is in between takes from one to another. In order to explain the notion of maximal paths over which are defined over subsets of actions, I am going to use this example of our model. So first of all, let's see that in this model is composed of 5 states that are, these are S0, S1, S2, S3, and S4. Now you can see labeling, so the states S0 and S1 are labeled with P, while the states S2 and S3 are labeled with safe, and the state S4 is also labeled with P. Now you can see that there are the transitions which go between states are labeled with actions. So in the in the set of actions we have A1, action 1, action 2, action 3, and action 4. Now what I am going to show you is how we define maximal paths over a subset of a set of all the actions, and this is defined in the following way. So let's take as a subset of all the actions only 3 actions: Act 1, Act 2, and Act 4, and let's look which maximal paths are in the set of all the maximal paths starting from S0. As you can see, there is only one infinite path, and this is the path which loops here an infinite number of times. So this is that one, loops over Act 1, Act 4, and there are two infinite sets of finite maximal paths, namely that one in which first there is a number of executions of Act 1 and Act 4, and then Act 1 and Act 2. And there is another possibility for a set of maximal paths. So when there is any number of executions Act 1 followed by Act 4, and then only action Act 2 at the end. The reason that we need to deal with maximal paths rather than with infinite ones is that we are going to look at restrictions of our paths to sets of actions which these paths are defined over. So even if we assumed at the beginning that our paths are infinite, if we restrict a set of actions, then we may get finite paths. So the idea is that in that case, which is different than from standard CTL, we are only looking at maximal paths. Let me now move to the part of this presentation in which I am going to give you the syntax of the logic and then to discuss its semantics. So the logic I am going to look at is called parametric action-restricted computation tree logic, and it can be viewed as an extension of computation tree logic with action and also with action variables. And just an extension with action gives this action-restricted computation tree logic, and extension with action variables gives us this parametric version, because then in addition to specify properties related to actions, we can also change the model checking problem into the parametric model checking problem, which is in fact about asking questions about valuations of our variables. So what we are going, for defining the syntax, we are going to use two sets. And the first set, which is the set denoted with act sets, is the set of all the non-empty subsets of the set of actions A. So in these actions are sets of actions are going to be used in the syntax as subscripts of our temporal operators, and as well as subscripts of these operators we can use also action variables, and this is all the action variables are in the set act var. The formulas of the language, parametric action restricted computation tree logic, are defined by BNF grammar. So in that grammar you can see that we can use proposition variables, we can use negation of formulas, we have logical OR, and we have three temporal operators, which is next step, G, which means always, and until. If you forget for a while about these red indices, the language you see in front of you is just the language of computation tree logic. However, as I said, we are extending it with two components. The first component is that alpha, which can be a set of actions, and the other component is corresponds to alphas, which can be action variables. Now, as to the semantics, I think that the best way to explain the semantics, rather than to show you formal notation, is to show examples. But before that, let me just mention the intuitive meaning of the operator, the E subscript alpha. It means there exists a maximal path over alpha. Now, if you think of alpha as a set of actions, then the intuition is clear. We are looking for paths which are over this set of actions which are in the set alpha, namely the path which uses only actions from this set. Does not need to use all of them, but all the actions which are in a path are from that set. Now, what about the situation when alpha is a variable? Now we are moving from trying to find out whether the formula holds in our model to asking a question. What are the valuations of the variable alpha for which our formula holds over a model? You will see that in a while on examples on the next transparencies. And these modalities X, G, U, these are standard next, globally, and until. And one may also use derived modalities, namely A alpha, which means for each maximal path over alpha, and F, which means in the future. As I said, the best way to understand the semantics is by looking at the example. So on the right of our here you have a model. The states marked with green are meant to be labeled with P, and the states marked with brown are labeled by Q. And you have names of the transitions, namely actions forward, left, right, forward, loop, etc. Now let's look at some properties. The first property says there exists a maximal path over forward and left such that always P holds. So one can find out that that formula holds in the beginning state because there is a path which is marked in green, which starts in that initial state. Let's look at another property. There exists a maximal path over forward and right such that P until Q. So you can also find out that we have such a path which satisfies that property. There are more examples how one can use variables. Namely, we can write a formula like that one, the first one, which specifies, which corresponds to infinite loops detection. I mean, that formula is true in a model in which there are infinite loops, but because we are using variables, we can in fact also ask questions for which valuations of the y variable we would have that formula true in a model, which means that we'll get an answer to a question over which actions there are infinite loops. The next formula is used for deadlock detection. In fact, that formula specifies that there is no deadlock. So if we use that formula together with the variable y, we can ask question for which valuations of that variable there is no deadlock. So obviously, if we know for which action sets there is no deadlock, then we obviously can also answer the question for which there is a deadlock. And our formula shows that situation can be even more complicated. Namely, we may not only have variables, but we may have different variables in one formula, and in that formula we have two different variables, namely y and z. And in order to explain what that formula in fact specifies, let me move to another example. So this is our model, as you can see at the top of the transparent, and that formula says that for each y reachable state, P holds and safe is Z reachable. So what does that mean? That means that we are in fact asking a question for each set of actions. P is always reachable and then Z is eventually reachable. So let's see which are possible assignments to y and z which make that formula hold. So the first assignment which you can see is that we can replace y with the set act 1 and act 4, and we can replace z with act 2. And why? Because there is only one maximal path over act 1 and act 4 over which P always holds, and you can see then from each state marked with P on that path there is a transition taking to a state where safe holds. Now let's see that there are assignments to that formula which do not make it hold. One of such assignments is, for example, Act 1 and Act 3. In order to find out that this is not the case, you need to see that there is only one maximal path over Act 1 and Act 3. Namely, this is the path, this is that path, yes. And then, as you can see from P, you can execute a transition, but it does not go to a state satisfying safe, and also it's not over Act 2. So that formula does not hold. So the general goal for this logic is to describe all the valuations of y and z which make, in this case, such a formula to hold. So let me now put it in a bit more formal framework, just give a more formal presentation of the goal we are aiming at. So we are given a model, we are given a formula phi from our logic, and let's define the set act vals, which is a set of all the valuations of action variables. Okay? Now our aim is to, for any formula of that logic, in this case of the formula phi, is to find a function which for each state assign a set of action variable valuations such that the following equivalence holds. V is an element of F with an index phi of S if and only if the formula phi holds in S under the valuation V. That in fact means that F phi of S contains all valuations that make phi hold in S. With the next theorem, I would like to tell you that we have about this logic two interesting results. So the first one is a good one because it says that the problem of deciding whether the non-emptiness of this function is decidable. The other result is less optimistic because it says that this problem is NP-complete. So that means that as soon as we believe that NP is not equal to P, we cannot find an algorithm of polynomial complexity which can be used for solving that problem. So typically, if we are dealing with NP-complete problems, we use for solving them symbolic methods. So for example, for CTL, there are symbolic methods which are based either on BDDs or on SAT in order to answer the question of whether the formula holds in a model. And in our case, this question is more complicated because we are not going to only answer the question about whether the formula holds in a model, but we would like also to say if that formula contains variables for which variables valuations that formula holds in a model. Typically, if we are dealing with symbolic implementations, algorithms, they rely on recursive equivalences which define formulas of our logic. I mean, for CTL, you can give a list of the recursive equivalences defining temporal operators in terms which is in fact used then for fixed point computation. So let's look what's going on here. So let's see first at the formula. There exists a maximal path over y such that always phi holds. I mean, phi holds over a maximal path if and only if phi holds in Q and either there is no outgoing y action which means that there is deadlock, so we are dealing with then a maximal path, or there is a Y action such then when it's fired, it leads to a state where EYG phi holds. So what you can see here, that this is in fact that gives rise to a fixed point equation, because that repeats here. So solving the model checking problem is in fact finding fixed points, and that's such a equivalence can be written not only for EYG phi but also for EY until. So we have recursive equivalences of our modalities over, as you can see here, that repeats here, that repeats, and for that we use these next step operators. One can use an implementation, and that is what we are doing in the tool Spatula, which first implements the next step operator, that one, and then compute fixed points using BDDs. That's similar to the case of CTL, computation tree logic, but we are not dealing with sets of states over which our formula holds, but we are rather dealing with indicator functions which correspond to saying for which sets of function valuations our formulas hold. So at this stage you already know about action synthesis, and this action synthesis has been implemented in our tool, which is called Spatula.